Good morning, everyone. We are going to perform the rise time budgeting. We know that the system rise time is for a non-return to zero is zero point 0.7 divided by the bit. And for return to zero, it the system rise time allowed is 0.35 by bit rate or the bandwidth of the receiver. Now the sources of delay, rise time delay in the system are the at the receiver, at the transmitter point, and also we have the rise time delays because of intermodal and intramodal dispersion. So the square root of summation of the delays across transmitter square plus the delay rise time delay at the receiver square plus the rise time delay because of intermodal dispersion square plus the rise time delay because of the group velocity delay square. Now we have to simply simulate this system. So what we need is the transmitter rise time, the receiver rise time, the rise time, and the modal rise time and the group velocity delay rise time. So we'll just take the input, select the input parameter. Now we have selected the rise time of the transmitter. We have selected the input terminal for the rise time of the transmitter, rise time of the receiver, rise time group velocity delay, the rise time model, and also the receiver band. Now additional thing that we want to know is whether it is an NRZ or a return to zero. For that we will be selecting going to ring an enum and select the enum. Now in this, you can just right click, go to the properties and go to the edit items. Here you can simply write your items as NRZ and insert one more value, return to 0 and press OK. So now it will have, we can see it will have two values, returns to 0 and non-return to 0. Now in this additional what we have done is we have selected the digital displays that is easier for us to note down the readings, and what we will do is we will also have one display for our readings, that is a display for the allowed system margin and the rise time delay because of the various components. System margin in nanoseconds, and this is allowed shifting and allowed system rise time delay in nanoseconds. And again we want to make a decision whether our design is correct or not. For that we'll be using a LED, and we'll be just going to the properties to change the off color to red to know whether our design is right or wrong. Now we have all the input parameters here. We'll just go and make the design. Go to the block diagram and make our circuit. Now what we have to do is implement this equation. For this we will be using our formula board. That's the simplest way of doing it. And select the formula. Now what all we have is, this is transmitter, then receiver, T model, and T GVD. Now we have square root of this square plus second terminal. We are simply writing the equation where the result is the square root of summation of square of the rise time of each component. Now our expression is correct. Press OK. Now we'll make the connections of the input terminals with the variables defined in the formula board. So this is GVD, then model. So our connections are made. Now what we will do is we will make it to connect it to this. Now it is in nanoseconds, and we will also find out depending upon whether it's a return to zero or non-return to zero, make a decision about the allowed bandwidth. For that we will be needing a case structure which will have, so the two cases which I have is return to zero and non-return to zero. Now, when it is returned to zero, we know what it is. It is returned to zero. It is TS system is 0.7 by bandwidth. So we will just say numeric divide. So it is, I just add a constant to the numerator. It is 0.7 and connect the bandwidth, receiver bandwidth or bit rate, and then connect the output to the, okay. Similarly, for the second case, it is 0.35. So again, I'll repeat the same. Take a divide, create a constant, in the numerator and receiver bandwidth in the denominator and connect it with the allowed. Now we know the system for allowed rise time of a system should be greater than the actual system rise time. Okay, I should not write it as margin. System rise time. Okay, now we have to make a comparison. So go to the comparison, select greater. So this value, the numerator is allowed and the output is connected to loop. So this completes our connection, and now let's check for the performance. So this is what we have. We see right now it is red and we have certain display. Again, we can add a digital display for our more clarity of the output value. Okay, now I'll just run it. So presently it is red because we can see the allowed is 0.14 nanoseconds and the actual system write time is 0.162. So we have, and if we check the values of our system, the highest being the receiver, we just reduce it to see whether we, yes, we can see that as I reduce it, the receiver, the conditions become satisfactory. So we can find out what kind of receiver should we use to get the required, allow the required bandwidth at the return to zero. I can again make it non-return to zero. You can see that for non-return to zero, you know our rise time has doubled. Allowed rise time is 0.28 and actual is 0.18. So we can have a higher values. So we can clearly see now the limiting conditions of allowed rise time for a receiver. So this is how we are able to simulate and comment on the system's satisfactory performance using the rise time budget. Thank you.